Hello everyone, the Algebra 2 Regents is coming up, and we here at Preppers want to make sure that you are prepared to succeed. We're going to take a quick look at the test format. There are 4 major clusters or units that will be on the exam. Number and quantity, which is with 5 to 12%, algebra 35 to 44%, functions 30 to 40, and statistics and probability, which is 14 to 21. We'll go more in depth in our in-unit reviews. You'll have 3 hours to complete this 37 question exam, which has 4 parts. First, we have 24 multiple choice questions, each worth 2 points for a total of 48. Then there are 3 short answer portions. Part 2 is 8 short answers, also with 2 points each, for a total of 16. Part 3s are worth more and can be multi-part. They're worth 4 points each, but there's only 4 of them, so Part 3 is equal in weight to Part 2. Finally, there's one last question worth 6 points. This one typically involves some sort of graph drawing, but it's pretty easy, so it should be a free 6 points. You'll notice that this adds up to 86 points, which is kind of a weird number. You'll have to remember that this Regents exam is positively scaled, so unless you get 100, you'll always get a higher scaled score than your raw score. You need a 77% raw or a 66 out of 86 to get into level 5, you'll need a 47 out of 86 for a level 4, and a 28 out of 86 or 30% to get a 3 and pass the exam. These numbers can change slightly from exam to exam, but it generally holds that you need around 1/3 of the points on the exam to pass. That's right, just 1/3 to get a 65, which is a passing score. Alright, let's get to some real material with Unit 1 of Algebra 2, Number and Quantity. So the first thing that we've got to know is the number system. We have a real number system below, and the 2 main categories we'll need to know are the rational and irrational numbers. Inside rational numbers, we see here we have integers, and inside integers we have whole numbers, inside whole numbers we have natural or counting numbers. Rational numbers are essentially anything that has a decimal that terminates or repeats, while integers require that the numbers beyond the decimal point are zeros, for example, negative 3.00. Behind the decimal point, there's just absolutely nothing. Whole numbers have to be equal to 0 or greater, so no negative numbers, and natural numbers are equal to 1 and greater, so the numbers you could physically count on your fingers. We see here that this is kind of overlapping. These circles here in the rational number set are overlapping. What that means is that any natural number is a whole number, is also an integer and is also a rational number, or any whole number is an integer and a rational number, but not a natural number. We can use this diagram to show what is what, and to classify the different categories. Now over here on a different circle we have the irrational numbers. Irrational numbers are simply numbers whose decimals do not repeat or terminate like pi or e. And next up we have some basic number properties. Alright, I'm not going to read through all of these, so you have to pause the video and write them down if you're taking notes, which is something we recommend doing. If you take notes, your brain will recall these concepts better on the exam and you'll have a higher score than if you're just passively watching. Anyway, you'll need to know these properties of radicals, rational exponents, logs, and exponents for your exam. Now that we've got this set, let's take a look at some polynomial division. Polynomial division is just like regular long division, except you use 2 polynomials as your divisor and your dividend, and you'll get a polynomial as your quotient. And it's easiest explained with an example. Let's say we're dividing over here 2x squared plus 7x plus 6, and we're dividing that by x plus 2. First, we're going to see what value we can multiply by this, by x plus 2, to cancel out one of these terms. And usually you'll want to cancel out the first term. So what could we multiply this by to cancel out 2x squared? So we'd want to have a negative 2x squared. Alright, so we're going to multiply x plus 2 by 2x, and we'll be able to cancel this out, because when we do long division, we want this to cancel out by subtracting. Alright, so we're going to take this, we're going to do 2x, we're going to multiply this by 2x, and we're going to get 2x squared plus 4x. We're going to subtract this, and we're going to get 3x plus 6 as our new polynomial. We're going to do this one more time. We're going to multiply x plus 2 by 3 to get rid of this 3x. And it just so happens that in this case, we got rid of the 6 as well, meaning there's no remainder. And in this case, a theorem called the factor theorem is going to apply right here. If there is no remainder, it means that x plus 2 is a factor of the polynomial. And in this case, it's really written as x minus a. So it's x minus a negative 2, not x plus 2, but obviously that's the same thing. Anyway, the remainder theorem, which is another theorem over here, will show what happens when we do have a remainder. Then the remainder will be f of a, or whatever we had left over, divided by the polynomial dividing. So let's say this was really like an 8 or 5 or whatever. Right, it would be like say 3 or 2 over x plus 2 would be our remainder. Another note on this topic, you do not need to do synthetic division on the Algebra 2 Regents exam. And if you don't know what this is, don't worry about it. And if you do, you can use it and you are allowed to, but you do not have to by any means. So next thing we're going to talk about is rational functions. Rational functions basically look like fractions and operate like fractions, but with polynomials as their numerator their numerator, and their denominator. So as we see here, fraction rules are going to apply. And if you don't know your fraction rules, you should pause the video to take a look at these, the multiplication, division, or you can do a quick Google search. Now, on the topic of rational functions and fractions, we're going to jump over to rationalizing denominators. This is an extremely important topic that's probably going to make up like a question or two on your exam, and you're going to need this skill if you have a fraction with a square root on the bottom. See, we have a square root right here. So what we're going to do to rationalize a denominator is we're basically going to take the square root, we're going to get rid of it, and we're going to put it in the numerator. Alright, and how we're going to do that is we're going to multiply both the top and the bottom by the conjugate of the denominator. Now, what does this mean? A conjugate basically just switches the sign. So if we have b minus square root c, we're going to multiply by b plus square root c. And again, we're going to do this on the top and the bottom, because by fraction rules, if we multiply the same numerator and denominator by the same value, we're going to get an equivalent fraction. So in this case, if this was really b plus square root c, we would be multiplying by b minus square root c. And when we do this, we're going to eventually end up with something that looks like this. And as we can see, the square root is on the top and there is no square root in the bottom. Now we're going to quickly jump into factoring, and then we're going to move over into our last topic, which is complex numbers. Our first example is when we have a clear greatest common factor. We're just going to basically factor that out by taking the greatest common factor, as we see here. 5x and 3x squared have a common factor of x, so we're going to take that out. We're going to get x times 5 minus 3x. This is pretty much the most straightforward form of factoring you can get. Now in example 2, we have a square number minus another square number, and we can rewrite this as the square root of the first plus square root of the second times square root of the first minus square root of the second. If that sounded a little complicated, let's take a look at this example. Our example shows that x squared minus 9, which is equal to 3 squared, is going to be equal to x plus 3 times x minus 3. And you can do the math here on your own to make sure this all checks out. Now, lastly, if neither of these are possible, or if you still need another example, you'll need to use the polyroots calculator function, which may be different depending on what calculator you're using, but you'll need to do that or figure it out yourself to find two numbers that multiply to the c in this form ax squared plus bx plus c, and add to this b. Make sure you factored out any greatest common factors before doing this step, as we saw in example 1. So here's an example. We're going to need to find two numbers that add to -4 and multiply to 3. Now let's take a look at the list of things that multiply to 3. Well, 3 is a prime number, so that's going to be 1 and 3 and -1 and -3. Alright, now we see that when we add 1 and 3, we get +4, so that's not our answer, but when we add -1 and -3, we're going to get -4, so those are our factors, and this is the factored form of the expression. We can check our work here by doing a little bit of box multiplication, and if you want to take a look at this or do it yourself, we should get the original value, x squared minus 4x plus 3. And you may also need to factor by grouping, which is a new type of factoring that was probably not introduced to you in Algebra 1. This is most helpful when you have a polynomial or function with a degree of 3 or greater. Alright, you're going to need to make two groups with a greatest common factor, then you're going to have to factor out your greatest common factor, and then you're going to have to simplify. And here we have x cubed and 2x squared. Now we notice that here we have a greatest common factor of x squared, so we're going to factor that out and we get x plus 2 as basically what we just factored out. And then we're going to do this again with a greatest common factor of -3 for these two terms, and we're going to get -3 and x plus 2. Now if it is possible to factor by grouping, the things that are in these parentheses must be the same. And when you take this, you're going to rewrite this, you're going to put it over here, and then you're going to basically add these two things together. So x squared plus -3 is x squared minus 3. Make those into a factor and then multiply by these two by each other, and that is essentially how you would simplify this first equation here to a factored form. Now our last topic is complex numbers. Alright, we're going to go over here. Complex numbers. The imaginary I is the basis of the complex number system, and it is equal to the square root of -1. What that means is that I squared, when we square both sides of this equation, I squared is equal to just -1. And if you want to learn more about that, try looking at your curriculum again or Googling a little bit more of an in-depth summary. Again, this is just a quick unit review, so you should have already heard of this concept. Anyway, we have complex numbers which come in the form a plus bi, where a and b are both real numbers, and b is the coefficient of a set number of i's. Rationalizing a complex number is basically just the same as a normal one. You're going to multiply the top and the bottom by the conjugate. And we see here we have c plus di, so our conjugate is going to be c minus di. And again, we have to make sure that if we have basically a rational function in complex form, we are going to have to multiply both the top and the bottom by that conjugate. And now we're moving on to the first part of Algebra 2's second unit, that is functions. This one's extremely general, but here's a topic-by-topic list of what this video will go over. We've got domain and range, composition functions, inverse functions, one-to-one and onto functions, end behavior, multiplicity, transformations, application of logarithms, and regression functions. First, we're going to define what a function is. Function should pass the vertical line test, meaning if you had a vertical line going through every single x value of the function, left to right, the function should only hit the line once for a given x value. Now in this second example right here, we see that a vertical line is hitting the equation twice at a given x value, so it is not a function. Function should only have one y value for each x value. Now let's talk a little bit about a function's main qualities and characteristics. Firstly, domain is the set of x values for which the function produces some sort of output, or the x values for which it exists. Rational functions domains, specifically, could be found algebraically. Their domains are everything but where their denominators are equal to 0, which is when they're undefined. Now this fancy notation right here with this r with two lines just means a set of real numbers, and this line in between basically means like another stipulation to the rule. And we'll talk a little bit more about that when we get to probability. So in this case, if we have the function f of x equals x minus 4 over x plus 2, obviously this is going to be equal to 0 when x is equal to negative 2. So our second stipulation here is that x is not equal to negative 2. So the domain is true. The domain is true when we have the real number set, so we're in the real number set, the set of real numbers, and when x is not equal to negative 2. So the domain is all real numbers if x is not negative 2. Alright, now let's take a look at radical functions. Other rules for radical functions, domains are functions like a square, cube, root function. These are all real numbers except when the radicand is less than 0. Alright, so here if we have the square root of x minus 5, this is equal to 0 when x equals 5 and less than 0 for all x is less than that. Therefore our domain is all real numbers greater than or equal to 5. Now let's talk about range. Range does not need to be found algebraically for the purposes of the Regents exam, but it's just the set of all y values that the function is defined for. Now let's talk about one-to-one and onto functions. One-to-one functions have no repeating x or y values, so something like a sinusoidal function like sine of x is not one-to-one since its y values, as we can see here clearly, are repeating. You could adapt the vertical line test to say that one-to-one functions must also pass a horizontal line test where no point would touch a horizontal line twice. An onto function over here is pretty simple, just means that all x values have a defined y value, so just most normal functions. Alright, now composition functions may be new to you. They're basically just a function inside of a function put together, and here's how we write them. This dot, by the way, is a hollow dot. It does not mean multiplication, rather it means f of g of x. Alright, and I'll show you what I mean with this example. If we have h of x is equal to f of g of x, and g of x is equal to 3x squared, and f of x is equal to the square root of 9x, that means that h of x is equal to the square root of 9 times 3x squared. Alright, let's take a look at that again. Alright, so we see how the 3x squared essentially just takes the place of the 9x inside of the f of x. That's kind of what we're looking for here, and here's just some work that would simplify that equation. Now we're going to shift over here, we're going to take a look at inverse functions. Alright, so when we've got an inverse function, they're pretty simple. They're basically what you get when you reflect any one-to-one function over the line y equals x. So let's just pretend that I'm a perfect drawer and this line is y equals x. When we reflect this thing here, y is equal to 3 to the x, then we're going to get y equals log base 3 of x. You can also solve to find inverse function by swapping the y and the x values of the original function. Alright, let's take a look at this. Let's say we have y equals 3x squared plus 5. We're going to swap the y and the x. We're going to get x equals 3y squared plus 5, do a little algebra, and we get the square root of x minus 5 over 3 is equal to y. And we use this notation here. It kind of looks like f to the power of negative 1. This just means inverse functions. Now we're going to switch gears and we're going to talk about end behavior and multiplicity. End behavior is pretty simple, and on the test, if you don't know what the end behavior of a polynomial is, you can just graph it. You'll see at the end of the functions will either go to positive or negative infinity, and that's pretty simple. But here's a quick trick to know. If the leading degree of your function is odd, like x cubed or x to the 5th, the ends will point in different directions. If the leading degree is even, like x to the 4th or x to the 6th, they'll point in the same direction. And if the coefficient of the leading degree is positive, like 4x cubed, for odd functions, it'll look like this right here, where we see it kind of looks like just like, y equals x, where we'll have, as we approach, as x approaches positive infinity, y approaches positive infinity, as x approaches negative infinity, y approaches negative infinity too. Alright, but if it's negative, like negative 3x to the fifth for odd functions, it'll look something like this other one right here, kind of in reverse, like y equals negative x. Even functions will have both ends going up for a positive leading coefficient and both ends going down for a negative one. Now, here's another thing. Multiplicity is basically just how many times something bounces, and we can see here as we go from 1, goes to 3, it kind of stretches a little bit, goes to 5, it stretches a little bit more, we go to 2, it's kind of normal, 4, it stretches, 6, it stretches, and that's basically all we need to know about that. Alright, now let's go to a big topic here, transformations. It's usually 1 or 2 questions on the Regents, and if your teacher didn't get through them through the year, they're pretty simple, but the best way to understand them was some practice questions. However, here's a brief review and some really helpful acronyms that I used when I took Algebra 2 to remember function transformations. Firstly, there's 6 different types of transformations that the Regents wants you to know. That is horizontal translation, otherwise known as horizontal shifts, horizontal dilations, aka horizontal shifting or scaling, shrinking or scaling, reflections over the y-axis and over the x-axis, vertical dilations and vertical translations. Let's start with the horizontal dilations, translations, and y reflections first, and you'll see why in a second. Firstly, right here is the equation for a horizontal translation. You're going to take the equation f of x and you're going to basically make into f parentheses x plus or minus a. Again, parentheses is important. We're going to see why in a second. But let's say we had x squared, then a horizontal translation would be, we put the 4 inside of the x, inside of the parentheses, right? Alright, now this would be a right shift, right? A right shift because we subtracted that number a. Each point is shifted by some value a as we see in this graph here. So this point kind of shifts here, this point shifts here. Alright, now again, let's take a look at that formula right here. The change is happening within the parentheses. Take note of that. And also realize that adding an a results in a leftward shift while subtracting an a is a rightward shift. Now let's take a look at dilations. Dilations shrink or stretch functions, and if we multiply them by some integer k, it'll get skinnier, and if we multiply them by some 1 over k, it'll get smaller. Again, this occurs within the parentheses as we see by our rule here, f of k of x, or f of 1 over k times x. Finally, our y-axis reflection is pretty self-explanatory. We take the red function, flip it over the y-axis, and you should have this background from geometry. Also, if you weren't already aware, the red function is the original while the orange or blue one are images. Anyhow, the equation for that is f of x becomes f of negative x. Again, inside the parentheses is where our change is occurring. Now we're going to take a look at some vertical stuff. It's all the same idea for a vertical translation, except adding an a moves it up and subtracting an a moves it down. Alright, so it'll look something like this. Now, this is different from what we had before. It is outside the parentheses. See how the x is unchanged inside that parentheses? Alright, it's not going to become like x minus 4 squared. It'll be x squared minus 4. Alright. Now, vertical dilations are essentially the same, except again the rule changes so it's outside the parentheses. So it's k times f of x and 1 over k times f of x. Alright. X-axis reflection is also similar. F of x becomes negative f of x, again outside of the parentheses. And we're going to flip over the x-axis. Now after all this, you might be wondering how on earth am I going to memorize all of this? Is just too much for me. Well, I got some simple acronyms for you. HIYA and VXVO. What do these stand for? We'll start with HIYA. It means horizontal inside the y-axis. Again, this doesn't really make sense, but when you think about it, any sort of transformation involving the y-axis, like reflection, and horizontal dilations and translations involves changing the rule on the inside of the parentheses. All 3 of those I just went over were inside the parentheses. Likewise, VXVO is vertical x-axis, vertical outside. All of these rules are going to happen outside of the parentheses. And you'll have to remember that translations always involves adding or subtracting an a, that dilations involves multiplying by k or 1 over some k, and that reflections involves adding in a negative. But that made a lot for me. I remember VXVO by thinking of the music company Vivo. Now, one last thing about transformation before we finish up with odd and even functions, regression, logarithms. The order matters. You always must perform your transformations in the following order: H, D, R, V. You can see what those stand for on my screen: horizontal translations, dilations, reflections, and vertical translations. If you don't do this, it'll mess up how your image is constructed. And I remember this by thinking helicopters do rise vertically. And you can make up your own little thing if you want, but that's just how I remember it. Alright, even and odd functions. A function is basically just called even if it is symmetric about the y-axis. So that's something like the cosine function or the function x squared. A function is called odd if it has 180-degree rotational symmetry about the origin. So f of negative x is equal to negative f of x for all x's in the domain. Right, so that's something like x cubed or sine of x. And you see this little fancy e just means like in. So all x is in the real number domain. Alright, 2 topics left. We'll go through these real quickly. Regression. This is different for everyone since we all have different calculators. If you have a TI Inspire, I recommend looking at our All You Need to Know for our Algebra 1 calculator guide. It's the same idea, same regression function. If not, just know how to recognize all these models. These 6 models here are very important, except for power functions, don't really show up very much, but those other 5 definitely important. And be able to use your calculator to find regression equations when you're given those data points. And applications of logs is our final topic. So we all know that this is the basic way to write a logarithmic equation right here, but here's some ways that that's actually useful and applicable in real life. And these may show up in word problems, especially on those 4-point or 2-point questions on your Regents. The first one is that we are going to show exponential growth and decay. So if we have this equation a of t equals p times 1 plus or minus r to the power of t, we can show exponential growth or decay by showing that p is our initial value, our start value, 1 is just a number kind of to represent like 100%, plus or minus, so minus is going to be a negative rate, plus is going to be a positive rate, and then our rate is always expressed as a decimal. So if we have something like 3% interest, right, that's going to be 0.03, and t is of course time. Now, compound interest can also be shown using this equation. The numbers mean the same thing except for n right here, which means the number of compounds per year. All right. So common compounding periods are monthly, quarterly, and daily, or yearly. It's how many times per year. We have 12 months in a year, 4 quarters, and 365 days, and of course 1 year in a year. So that would just be 1. Now, the last thing we have today is continuous compounding, which requires the use of the number e. And yes, it's the number e. It's a constant that's approximately equal to 2.72 and is the limit, if you know what that means, of the function 1 plus 1 over n to the nth as n approaches infinity. In other words, as this equation right here has n getting infinitely bigger, that's what that's equal to. And you don't need to know that, you just need to know how to use this equation right here when given a situation with continuous compounding. Now that we've discussed most of the major functions on the exam, it's time to take a look at the final function family that's part of Algebra 2, that is, trigonometric functions. We're going to go over radians and degrees, trig functions, the unit circle, special triangles, identities, inverses, graphs, and parts of trig functions. First, let's start off by identifying the way that we measure angles, that is, radians and degrees. These equations are both in your reference table, so you don't need to memorize them, but to go from degrees to radians, simply multiply by pi over 180, and to go from radians to degrees, multiply by 180 over pi. Now, let's get into some real trig. Algebra 2 involves the 3 primary trig functions, that is, sine, cosine, and tangent, as well as the reciprocals, that is, cosecant, secant, and cotangent. Alright, these are a little bit less common, but you still need to memorize all of these functions. Again, most of this trig unit is memorization. Now, since sine theta is defined as y over r, cos theta is x over r, and tan theta is y over r, they can also be called opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, respectively. This can be memorized as SO, COT, TOA. You may have heard this acronym before. The reciprocals are of course the exact same thing, but reciprocal. R over y, r over x, and x over y. Now, if that sounded confusing, let's look at an example triangle right here. Here, let's focus on this orange angle right here first. This here is the side adjacent to the angle that is not the hypotenuse. Again, the longest side is of course always the hypotenuse. The hypotenuse is always the longest side. And again, this also has to be a right triangle. We are looking at right angle trigonometry only in Algebra 2. Now, we have the hypotenuse, we have the adjacent. That means that the last side must be the opposite angle. Alright, it's also opposite from the angle. We see it's not touching, these two sides are touching the angle, this side is not touching the angle. Now if we're to focus on this blue angle here, that means that this side becomes the opposite because this side is opposite from the blue angle, while this one becomes adjacent because this one is next to the adjacent, and the hypotenuse of course stays the same. Now let's see how our trig functions like this can relate when we have some real numbers involved, that is with special triangles. The 2 special triangles, that is triangles with common angles like 30 degrees, 60 degrees, and 45 degrees, are the 2 square root 3, 1 and the square root 2, 1, 1 triangle. Let's look at the first one right here. Alright, if we wanted to find sine of 30 degrees, which is the same thing as saying sine of pi over 6, right, we're going to go to the 30 degree angle, which we have right here, and then after we do that, we're going to find the opposite side of the hypotenuse. Alright, which one's the hypotenuse? It's obviously going to be this one. Which one's the opposite? It's going to be this one. Right? We know the hypotenuse side is the longest, of course, and the opposite one's just opposite the 30 degree angle. So since we know that sine is opposite over hypotenuse, we're going to have our opposite, which is 1, over our hypotenuse, which is 2. That means it's 1/2. If we do this for the other triangle, let's say we wanted to find sine of 45 degrees, we're going to focus on our 45-degree angle. We have our opposite, we have our hypotenuse, so it's 1 over square root of 2. If we want to radicalize this denominator, which we learned in a previous unit, we simply multiply both the top and the bottom of the fraction by square root of 2. Obviously, square root 2 times square root 2 is simply 2, and the top becomes square root 2. Alright, we're going to get into what these y's, x's, and r's that I mentioned up here mean in a moment, but for now make sure that you have these triangles memorized. These special triangles have to be memorized so that you know what those values are. And you can use your calculator to find the sine, cosine, tangent, cosecant, secant, or cotangent of any angle, but it'll spit out a decimal, and sometimes the question will ask for the answer in exact form, like this over here, this square root 2 over 2, which your calculator will not give you. It'll just give you, again, another decimal. And these angles, 30, 60, and 45, are the only ones you're ever going to need to know exact values for. You know, with other angles you can use a calculator, but if you're asked for an exact value, you have to provide it like this, with a square root in there, and your calculator will not do that for you. Now let's take a look at some identities. These are basically just facts about trig equations. First, we have that sine is 1 over cosecant, and this makes sense since they're reciprocals. Therefore, these relationships carry on for the other 5 trig functions, as we see here. Now, tangent and cotangent has some other special properties. Tan theta is equal to sine theta over cos theta, and cotangent theta is equal to cosine theta over sine theta. I have a little proof below to show each one. You can just take a look at that and pause the video if you need to. We also have the Pythagorean identities. You may remember Pythagoras from the Pythagorean theorem, but these are his identities. Now, you just need to memorize that these are true. Right, you need to memorize that these are true, and they may pop up in the exam, they probably will not. But for example, a question might ask you, say, what's the value of cosine squared theta, and it'll give you the value of sine squared theta. Well, you just plug this value in here, you use this, and then you find this algebraically very simply. Alright, and now you still may be wondering, where did all that x, y, and r stuff come from? Let's regroup and take a look at that again. Alright, we're going to look at a circle, which may be weird since you thought we were talking about triangles, but specifically we're going to be talking about a unit circle. And what that means is that the radius of the circle is equal to 1 unit. 1 unit. Alright, let's do a little bit of a deep dive into what that's going to mean for us. If we draw a radius, or several as I have here, all of these lines here, they're all radii. Right? If we draw one of these radiuses, what we're going to see is that we have a triangle that's made between the y-axis, the x-axis. Let me draw the illustrator. The y-axis, the x-axis, and the unit circle. Alright, and this is a radius. Now the radius is of course going to be the hypotenuse of this triangle. Right? It's the longest side, of course. Okay? But how do we know where to draw these triangles, and how does this really help us? Well, here I've marked a bunch of different angles in both radians and degrees. If I wanted to find sine of 30 degrees or pi over 6, it would be pretty simple. Alright? We're just going to find the degree, so this theta, right? So let's say that this angle here is our 30 degrees. Right? That's 30 degrees. Now when we have that 30 degrees, we're just going to use the y value of this point where we intersect and the x value. So this is some point, right? This is some point x, y. Right? And what we're going to use is that this is y and this is x. Right? And then this is 1. Now we know that if we wanted to find the sine of 30, we're just going to do the opposite, which in this case is y, over the hypotenuse, which is r, or 1. This is where y over r comes from. But we know what this y is, right? We know this from our special triangles, that this y is just going to be 1, and then that would be 2. Of course, we have our radius as 1 here, so this would really be a half. So what we should get then would be, in this case, we would get 0.5 over 1, which is equal to 1 over 2. Now, let's think about what would happen if we were given the sine of some value, but you did not know the angle. In that case, we would use the inverse trigonometry functions, which are arcsine, which is also written in this type of notation, arccosine, and arctangent. Let's see what I mean here. Let's say we're given that sine of x is equal to 1/2. We're going to use our inverse trig function. See that we had the little -1 kind of thing up there? And we're going to basically swap it. So we put the 1/2 here, we put the x here. Alright, now we're going to have arcsine of 1/2 is equal to x. And we saw before this was 30. But if you put this into your calculator, it would give you this value, this to be 30. If you were in degree mode. If you were in radian mode, it would give you a different answer, give you pi over 6. I also included some graphs of the functions. These all have restricted domains and ranges because, as we mentioned in a previous unit, inverse functions must be one-to-one functions, and normally trig functions are not one-to-one, as we saw earlier. But they are one-to-one if we only draw them for a certain domain. And to sidestep a little bit, here's how we might draw an angle. This is really the proper way. We have the initial side here, we have the reference angle here, and we have the terminal side here. Remember that if you're trying to find the arcsine or arccotangent or tangent or whatever of another thing, you may need to add or play with the angle to figure out exactly what quadrant you're supposed to be in or what quadrant you're finding in. Because these are restricted to different quadrants, right? You may need to find the angle in one quadrant, say this quadrant here, and then add 90 degrees, right? Because if we find the angle here, these are the same angle, but we would need to subtract this from 180 to get what this angle is. Now, if that sounded a little bit confusing, make sure to go back to look at your notes. Again, this is a unit review video, so you probably should already know how to do this. If you don't, make sure to check out our topic videos or go back and look at your notes. Now, let's move on to what an actual trig equation would look like. The three common ones that you'll see come in this format here. We have y equals a sine or cosine or tangent or whatever of b2 minus times x minus c plus d. Alright. Now a is the amplitude, which is 1/2 times the max value, y value, minus the minimum y value, absolute value of that. b1 is the trig function used. b2 is the frequency. Note that also the period is 2 pi over the frequency. C is the horizontal shift, with a positive c being a right shift and a negative c being a left shift. And d is the vertical shift, with positive being up and negative being down. Alright, now to end the video, let's look at this function up top to see if we can determine what its equation is. And first, we clearly see that this is a sine function. Even if we didn't see this sine function down here, we should be able to recognize what a sine function looks like. Remember, sine starts at 0, and it kind of goes up and then down and then it goes again, whereas cosine will start at 1 and then go down. Tangent looks completely different, and that should be pretty easy to recognize. Anyhow, we can see on our unit circle, let's relate some concepts here. We can see on our unit circle that these functions are going to match up with the unit circle. So let's say at 0, right? Cosine x is at its maximum value. It's at 1 over 1, right? Because there's no triangle formed. It's just a line. It's at 1 over 1. And that's at 0 or 2 pi. And we see over here in this graph that at 0 and at 2 pi, cosine is at its maximum value. Likewise, sine of x is at its maximum value at pi over 2. And if we go over back and we look at our unit circle, it's at its maximum value at pi over 2, where y over r is just 1 over 1. Right? Anyway, we know that it's sine x. Now our amplitude is going to be 1/2 times the absolute value of the max minus the min value. The thing between those two is going to be the midline. So this right here is our line. We're going to call it the midline between the two. Alright, because this is our min, this is our max. And we can see, what is our amplitude? Well, we're going to go 1, 2, 3 up. So our amplitude is 3. And again, another way you could calculate that is 1/2 times the absolute value of 8 minus 2. Of course, is 1/2 times 6, which is 3. Alright. Now, the next thing we have here is the frequency. In these 2 pi's, we are completing, it looks like, 2 cycles. So that means our frequency is going to be 2. Now, the horizontal shift it's very interesting. It looks like we are shift pi over 2 to the right. Because when we are at 0 here, we're going down instead of up. Where we should be is right here if there was no horizontal shift. That means we went pi over 2, right? We went pi over 2 to the right. Therefore, right, because we went this way. So that's our that is our horizontal shift. And finally, our vertical shift, it looks like we're 5 above the x-axis. That means our vertical shift is 5. And given this equation, that means we're going to write our amplitude is 3, function is sine, right, times 2, which is our frequency, times x minus our horizontal shift, which is pi over 2, plus 5, which is our vertical shift. 35 to 44% of your Regents examination will be on this unit, that is algebra. We're going to go over linear equations, quadratics, and sequences/series. There's also a super important topic, focus and directrix, that will definitely be on your Regents exam and has been for years now. We'll look at it, but firstly, let's look at some linear stuff. Now, linear functions or linear equations are just functions with a degree of 1 and are always straight lines when drawn in a graph, and they always have a clear slope too. Right here we see some examples of a positive slope, negative slope, zero slope, and undefined slope. Slope, which is also known as the average rate of change, or AROC, change in y over change in x, rise over run. It can also be found by taking the y value at b at some x value b minus the y value at a, some x value of a, over the b minus a value. And if this didn't make sense, think of it this way. B and a are different x values, and we plug in those x values to an equation f of x, we're going to get some sort of y value. So this was really just saying change in y over change in x in a different way. Now let's take this example here. We have 2 points, that is 3, 6, and 0, 4. And our change in y here we see is positive 2, our change in x is positive 3. So our slope is 2, 3, or 2/3, because we have that change in y over change in x. Now when we see a linear equation in the form y equals mx plus b, right, m is the slope and b is the y-intercept, or it might be the starting value in a word problem. Now, point-slope form, as seen in the second thing right here, uses the same m for slope, but includes some sort of random point in the line. Now, let's say here we could take that point we had earlier, 3, 6, to take the places of y1 and x1, so we would get y minus 6 equals 2/3 times x minus 3. Now, this should all be reviewed from Algebra 1, but what's new in Algebra 2 is 3-variable linear systems. If these show up in a multiple choice question, what you should be doing is just using the lin-solve function or calculator, and we have another video to that. Be sure to check it out as a calculator guide to Algebra 1 and Algebra 2 Regents examinations. On short answer questions though, you'll be required to show your work, so just doing a little bit of a calculator hack is not going to help you. Here's a 6-step plan that you could do that. The first thing you're going to do is group your first and second equation, and then you're also your second and third equation. Then you're going to eliminate the same variable from both systems, consolidate both systems to one equation, use those new equations you just got to make a new system, then eliminate another variable, and then once you find that and solve for that variable, you're going to go back and find the other two. And that sounded pretty complicated, so let's go over it with a little bit of an example. Let's say I have this 3-variable system, x plus y plus z equals 1, 2x plus 4y plus 6z equals 2, negative x plus 3y minus 5z equals 11. So we're going to split it off again. We had the first group here, we have G1, our first group is the first two equations, we have G2 as our second two equations, and if you do not know how to solve a 2-variable system of equations, then you should probably go back and review your notes, or take a look at your Algebra 1 stuff, because this should all be reviewed from Algebra 1. Now, once we take this first group here, we're going to multiply that top equation by -2 so we can cancel out the x's. We're left with 2y plus 4z equals 0. Likewise, we're going to multiply this one by 2 so we can get rid of those x's. We're going to get 10y minus 4z equals 24, and we see we've completed this step right here. We have eliminated the same variable from both systems. We have eliminated the x variable. Now we're going to use these two new equations that we just got here. We're going to make a new system of equations that is 2y plus 4z equals 0 and 10y minus 4z equals 24. We're going to solve for one of the equations. We eliminated this 4 right here just by adding them together. We're going to get that y equals 2. And now that we have that, we can go back and use this equation that we just had here to solve for z. We get z equals -1. Then we're going to go back and take this equation all the way back up here that had the 3 variables pretty plainly. And we're going to insert the things that we know that are now equal to y and the thing that we know is now equal to z. And we're going to get that x is equal to 0. So our final solution here is that y equals 2, z equals -1, and x equals 0. Alrighty, next up is quadratics. So we are going to start with quadratics right over here. Quadratics are polynomials with a degree of 2 and have a U or a horseshoe shape. Their standard form for an equation is right here. We have y equals ax squared plus bx plus c. They are also symmetrical, and their axis of symmetry is right here, where we have -b over 2a. b and a are the same values that we see here in our standard form equation, right? If your quadratic is not in the form ax squared plus bx plus c, where a, b, and c are all integers, you need to take a look and reevaluate and then manipulate your form or your equation algebraically so you can get it into standard form. Now the sum of the roots and the product of the roots are illustrated by these two equations, again using the same b and a. Roots, of course, are just your x-intercepts or your zeros. Let's also take a look at the quadratic formula. This is a formula that is given to you on your reference table, but it is very helpful to have memorized. Not too hard to memorize. If you haven't found the quadratic formula song, you might as well give that a Google. And Anyhow, the discriminant is the most important part of this formula since we've already gone over what this means. Again, this is the axis of symmetry. This discriminant is basically just this little bit here, b squared minus 4ac. What this does is it determines the number of real roots and the nature of those roots. So if you plug in those b, a, and c from before, and it is negative, that means there are no x-intercepts, no real x-intercepts, no real roots. So you have complex roots, but there are no x-intercepts, no zeros. This also means that basically your function never hits the x-axis, so it has a y-intercept that is not 0. Alright, if it's 0, then we have one x-intercept. If it's 2, we have two x-intercepts. And if that number, this number here, ends up being a square number, then when we apply the square root function, it's just going to become a regular integer, which means that we would have a rational root. But if it wasn't, then we would have a square root up here still, and it would be an irrational root. And now what you've of course been waiting for, the torture of focus and directrix. This is on every Regents exam and is usually a 2 or 4 point question. Every year it's on there. They are removing this from the curriculum for the 2025 to 2026 school year, but until then, we are stuck with focus and directrix. Now, the focus of a quadratic is essentially a point on the line of symmetry that is the same distance, so this distance here is equal to this distance from the line known as the directrix. Let's list this line right here. These are both perpendicular to the line of symmetry, and this distance right here from here to here and from here to here is known as p. So from here all the way down to here, that would be 2p. Alright, and this occurs at the same x value as the turning point or the min or max. Now if we have a quadratic, we can write it in this thing called vertex form, which is right here. Alright, you just have to do some more algebraic manipulation to switch from standard form to vertex form or whatever form you would have. And what we do is we write the vertex in the form hk, with h being the x value of the turning point right here, and k being the y value. Right? The equation to find the focus is h comma k plus p, since the point. The directrix is y equals k minus p, and the vertex form is y equals x minus h squared over 4p plus k. Alright, this all applies for only a vertical parabola, so when the things are going vertical, they're going up or down or whatever. Now if your arrows are going left to right, then we have a horizontal parabola, and these are the rules. We're basically just going to switch the h's and the k's, the x's and the y's, because we are going in the other direction. You can take a look, pause the video, and write some notes if that is what you need to do. But we are going to move on to a practice problem. I usually don't include these in unit summary videos, but this is important to consolidate our knowledge. This is from the June 2023 practice Regents. There was a similar problem on the January 2024 Regents, but I like this one better. So our answer is 2. I'm just going to give that to you straight away. But if you want to pause the video, which I highly recommend doing, and check your work, see what you get. Alright, so the directrix is y equals 4, and we know that this means it's a vertical parabola because only a vertical parabola has y in it, right? A horizontal one would have x. Alright, so we know this is a vertical parabola. We know that y equals k minus p from our work over here. That means that therefore 4 equals k minus p, and k equals p plus 4 if we do a little algebraic manipulation. Likewise, if we use our point here from the focus and we have h comma k plus p, we know that h is 0, right, because it just has to be 0. And we know that k plus p equals 6, which means that k is also equal to 6 minus p. Now, these are both equal to k, so we can set them equal to each other, and we get that p equals 1 after a little algebra, which also means that when we plug p back into here, we get 6 minus 1 equals k, so 5 equals k. Now we have that final equation. We have our h value, we have our k value, we have our p value. H is 0, p is 1, k is 5. We can plug that into this equation here for vertex form. We get this equation, we do a little algebraic manipulation that looks a lot like our answer right here. Alright, final thing, we've got sequences and series. Sequences are lists formed with terms, and series are basically just the sum of those terms. And there are two types of sequences, arithmetic and geometric. Arithmetic sequences are like linear equations. You just add or subtract to get to the next term. You might have heard these as now or next equations. Geometrics are like exponential. You multiply or divide by some sort of ratio or number to get to the next term. And unlike equations, these are only defined for the integers. They are not defined for decimals or anything in between. So while a linear equation like y equals x is defined for something like x equals 1.5, it would not be defined like that for an arithmetic or a geometric sequence. Alright, there's two different types of equations for sequences. We have explicit types and recursive types. So the explicit one is used to find the nth term, while the recursive is used to find the next term. Alright, Here are the equations to those below in a little bit of a table. Alright. Note that D is the common difference between terms, which is basically the amount you need to get from one term to the next, while R is the common ratio, which is the amount that you need to multiply or divide by to get to the next term. Pause the video and take a little note on this if you want to write these down. These are not on your reference table. Now, finally, we have sigma notation. Sigma notation is pretty simple as well. We're going to use the sum symbol to add up terms in a sequence, and you can use your calculator's sigma notation to easily find the sum of a sequence. And here's an example if I were to do it by hand. We see here that this 4 means that our last term is 4. We saw that from this right here. Alright, we see that 2 is our first term. We see this right here. And we said this is the equation that we need to use to plug this into. So we're going to have to plug in 2 first, then we're going to plug in 3, and then we're going to stop at 4. So we put this all together, we put it in the equation, then we get that our final answer is 21. Your calculator can do this for you. Now, geometric series formula. This is pretty easy. Just find it on your reference table. This is the only thing that's on your reference table that's super helpful. Just plug in the same variables as we had down below and it will give you your answer. This unit was definitely a lot, but the main things you got to remember is you have to know your Algebra 1. You have to know things like completing the square I did not go over, stuff like that, factoring, etc. We talked about that a little bit in our first unit, but make sure that you know these concepts and have them fundamentally down so you can learn things that take it a step further, like our 3-variable linear systems and our focus and directrix. We've arrived at the final unit for Algebra 2, Statistics and Probability. This makes up 14 to 21% of your exam, so usually you'll see 1 or 2 multiple choice and 2 or 3 short answer problems. We're first going to talk about the types of studies. We have sample surveys, observational studies, and controlled experiments in this course. Sample surveys are like online polls. Experimenters take a randomly selected sample of answers from a larger survey and analyze them, and they cannot draw inferences, but they can draw generalizations from their results. In observational studies, we have a lot less work on the part of the experimenter, and they're often a lot more cost effective. They simply look at something that's already happening and analyze the results of whatever that treatment might be. As such, this is a non-random treatment and selection. From this, one could find causation, but not a greater generalization because the results of this treatment only represent what is true in an observed population, not for the greater world population. Lastly, there's controlled experiments, which involve active experimenters who randomly assign different groups of people to treatment groups. Participants may or may not be randomly selected to participate. For example, brain MRI studies often involve some form of payment to the surveyed peoples because of a risk of radiation poisoning. From these studies, a generalization can be made if the participants were randomly selected, otherwise only an inference can be concluded because of potential bias. Studies can also be used single-blind or double-blind. In a single-blind experiment, the participants don't know which side of the experiment they're on. For example, in a vaccine study, participants might not know if they got, for example, a placebo or a real thing. This eliminates some bias and mistaken results. Double-blind experiments have this too, but the experimenters themselves don't know which group is which until after they've analyzed the data. Using the previous example, they would analyze the data without knowing which group got the placebo and which group got the vaccine until after they had collected and fully analyzed the data. This would eliminate the most bias. Now, good experiments always involve 3 things. The random assignment of treatment, such as in a single or double-blind experiment, have a lot of participants, and include a control group. Let's dive in a little more complicated statistics. Firstly, you should know terms such as standard deviation, mean, mode, and median from Algebra 1. In this case, we're going to define mean and standard deviation using different variables depending on whether we look at a whole population or just a sample. We're going to use an x with a line over it for a sample mean and mu, a Greek letter, for the population mean. Standard deviation is an s for sample and a lowercase sigma for population. We'll apply these definitions throughout the next couple of minutes. The first thing we're going to need to learn is what a normal distribution curve looks like. A normal distribution is symmetrical, and 68% of the data, as we see here, is within 1 standard deviation plus or minus 1 standard deviation from the mean. 95% is within 2, and 99.7 is within 3. If you're given a specific individual and need to find the percentile that it represents within this distribution, you'll want to use the norm CDF function on your calculator. Because every calculator is a little bit different, be sure to look up how to use the norm CDF function on your own personal calculator. One last thing to know about this diagram is that it is a perfectly distributed curve with the mean, mode, and median representing the same value, the midline of the curve. We have a few more equations to go over before we move on to probability. First thing is confidence intervals. A confidence interval is a measure of how good your data is, and it can be calculated using this equation. Ci is equal to the mean plus or minus z times lowercase sigma over the square root of n, where n is your sample population, and z changes based on what your confidence level is. If you want to find a confidence level of 90, you'd use 1.645, 95%, 1.96, and 99%, 2.575. These three values must be memorized for your Regents exam, and there is no way around it. Now let's say you want to calculate the margin of error. The margin of error is greater when there's less people. This makes sense. Just think about it. If you have a survey with a lot more people, it's going to be more accurate than a survey with less people. The margin of error can be calculated by multiplying z times p times the square root of p times 1 minus p over n. This z is the exact same z that we used right here, and we would use these exact same values. A different z is found in z-scores, which are just used to find how many standard deviations a value is from the mean. We're going to take those differing values from earlier and create two equations that essentially mean the same thing. This first one is for samples, and this first one's for population, but again, these variables essentially have the same meaning, just for different sample versus a different population. Alright, z is equal to the selected value minus the mean over the standard deviation value. Same thing here. And again, you can find standard deviation values using your calculator from Algebra 1. This just about finishes statistics. If this seems a little bit abstract, don't worry, because on your Algebra 2 exam, statistics should be pretty clear and they shouldn't involve too much guessing. They should be pretty concise as well, and you shouldn't need to show too much work. Now into probability, which at this stage is just common sense and again memorization. The first expression here is set as the probability of A or B, and this is just the notation we use. The U right here means union. It's the same deal here. This means the probability of A and B occurring, and given that A and B are different events, probability should always be written and calculated using fractions as well. This, by the way, this upside down U means intersection. Let's finish this up. We've got the probability of a complement, which is the probability that an event, say, let's call it event E, does not happen. This is written as P of event, or E prime, is equal to 1 minus P of E. So basically, 100% probability minus the probability the event does happen is, of course, the probability that it doesn't happen. And this just really makes sense. Again, going back to the idea that probability in Algebra 2 is really just about using common sense. Now, mutually exclusive events have nothing in common and don't affect each other. This means that the probability of A and B separately is essentially the same as the probability of if both of them or either of them happen. And independent events means that the outcome of the first event, let's call it event A, does not affect the outcome of event B. Right? There are three ways that we can prove this, as we see here. Using conditional probability is probably easiest, and we'll learn that in a second, but that's just basically where we have this P of A, a little line, B, and then in parentheses. Now, a dependent event is obviously just the opposite of an independent event, and it means that the outcome of the first event will affect the second event. This is how we calculate that. Again, let's look at conditional probability. This is written like this. It is the probability of A happening given that B has already happened and we know the outcome of B, and we can write it like this. At the end of the day, these are really just formulas that you can memorize, or you can just think about it on the exam. I mean, using common sense, you can usually derive them yourself, and just think about, again, this example of complements. The probability of 1 is just 100%, right? So subtracting the probability that something will happen will just give the probability that it doesn't. We here at PrepWorks wish you good luck and a high score on the Regents exam.